if I have a double bond that's conjugated in with a carbonyl, that has some special reactivity to it. Nomenclature-wise, that's called an alpha-beta unsaturated compound. We've used that kind of nomenclature before. Alpha is next to, right? So if a compound is a carbonyl, the alpha carbon is the carbon next to the carbonyl carbon. Beta is beyond that. So it just goes by the Greek alphabet, alpha, beta, gamma, delta, epsilon, so on. So if it is alpha beta unsaturated, that means there's a double bond that is conjugated in with the carbonyl. Okay? And in a normal carbonyl, right, it's polarized with an O- and a C+ as a resonance structure, but there's another resonance structure when we have alpha beta unsaturated. The double bond can shift over towards that C+, making the beta carbon have a plus on it in a resonance structure. So in this compound, both the carbonyl carbon and the beta carbon are electrophilic. Right. So that's the nomenclature we use. The carbonyl carbon and the beta carbon are both electrophilic. So depending on the nature of our nucleophile, we can do two types of additions. We can do a direct 1,2 addition, right, where nucleophile adds and then we protonate the alkoxide, for instance. So we've added two things just adjacent to each other. So that's a 1,2 addition. Conjugate addition, or 1,4 addition, means the nucleophile adds to the beta carbon, and that sort of sets off a cascade that pushes the CC double bond over between the alpha and the carbonyl carbon, and then that pushes one pair of electrons. It kicks them up onto the oxygen there. So what we get is called an enolate ion. Okay? It resembles the enol that we've talked about before, where we have an O-, sort of an alkoxide, but attached to the CC double bond. And there are two resonance structures, right? The O- and the alpha C-. Okay? So in the alpha C-, there's a CC double bond. Okay? So in the other one, the alpha and the carbonyl carbon are double bonded, and we have an O-. So those three atoms, the minus switches its position in there. So when the enolate ion is protonated, our sole product is a ketone. Okay? You could think of it, if you wanted, as forming an enol, OH, right? Something like that. But enols are not isolated. So if you like to think of an enol as forming, that's fine. That's actually how we get the name 1,4 addition, right? Where the nucleophile has added, the H has added, right? That's our 1, 2, 3, 4 addition. Okay? But what happens? The enol rapidly tautomerizes to the keto form. Okay? This H attached to the O becomes attached to the alpha carbon right there. So if we look carefully at our product, what we end up with, right, the nucleophile attacks the beta carbon, okay, then the alpha carbon is protonated. Okay? So it's really sort of like a 1,2 addition, but not at the carbonyl. Okay? It's like a 1,2 addition at the double bond. But careful, that only works with a double bond conjugated in with a carbonyl. Okay? Regular double bond is not reactive to nucleophiles. Okay? Has to be alpha, beta, unsaturated carbonyl compound, okay? Where we can essentially add across that double bond that way. But it's very important that you know that the key intermediate here is this enolate ion. And you'd be able to draw the arrows, right, going from the nucleophile to the beta carbon, the double bond going between alpha and the carbonyl carbon, and then the C double bond O kicking up onto the O-. Okay? So that's called conjugate 1,4 addition. Turns out that most nucleophiles will undergo conjugate addition if I have an alpha beta unsaturated ketone. So that's the case with most of the things that we've talked about in this chapter. If I have, for instance, a primary amine, right, that will undergo 1,4 addition, right? Where we had originally this is 2-cyclohexenone. We still have those two H's, but now I have an additional H on the alpha carbon. So our addition occurred between the alpha and the beta carbons. Okay? And it's just a matter of proton transfer and so on in order to get it there. So we end up with a neutral product, which is a beta amino ketone. The nucleophile has added to the beta carbon. We've protonated on the alpha carbon. It was by way of a proton transfer that occurred. The imine, right, which would have been product of 1,2 addition, the imine does not form if we have this alpha beta unsaturated. It's actually easier for a nucleophile to approach the beta carbon that way. The product ends up being much more stable as it is, right? Because we've gotten rid of a double bond. Beta hydroxycarbonyl compounds can be formed by adding water to an alpha beta unsaturated compound. So in the presence of a large excess of water, you can imagine this mechanism right here. Here's a carbonyl, here's alpha and beta with a double bond. Okay? You can envision at least the first step of what would happen here. Nucleophile attacks beta, double bond shifts, kicks up on the carbonyl, then we protonate alpha. Here's our alpha and beta still, right? We added the hydrogen, we added the OH, right? It was essentially the addition of water across that double bond. So you can envision the steps of the mechanism that would be required to do that. If we have a carbon nucleophile, we can also do conjugate addition, right? We can have R minus add to beta and then protonate alpha. But in order for that to happen, our carbanion, our C minus, has to be one of the more stable carbanion varieties. So if we think back to our alkyl halide chapter, you'll remember that we could form a stable C minus by reacting an alkyl lithium compound, right? I mean, we start with an alkyl halide, react it with lithium, we get an RLi, which is essentially R, which is a C minus and an Li plus. Okay? But then, if we react that with copper iodide, we get 2 R groups attached to a copper, which makes a Cu minus, and then Li plus as the counterion. That's called a lithium dialkyl copper compound, or a Gilman reagent. So you can draw that all kinds of ways. We can call that R2CuLi, for instance. Right, 2 R groups. But essentially what it is again an R minus, right, RCu, right? It essentially reacts like that. So that means if I have an alpha beta unsaturated carbonyl compound like that, if I react it with that gentle Gilman reagent, right, this is dimethyl copper lithium, right, or lithium dimethyl copper, right, whatever you want to call it. We add one of those methyl groups, right? We have 2 of them in this copper compound, but only one of them is nucleophilic. Okay, we add one of them, and then end up with an extra H. On the alpha carbon. Okay, so that's conjugate addition. That's 1,4 addition. Okay, the nucleophile has added to the beta carbon. If we do it with a strong carbon nucleophile, so Grignard or lithium, right, what we end up with is product of 1,2 addition. Right, this Grignard reaction happened just as if this double bond here didn't even exist. And our workbook, right, our Pogel book, had a great explanation for why that was. Make sure you read through that if you didn't get to it in class. Essentially what happened is if we have a Grignard reaction, or a Grignard reagent, RMgBr, those are very high in energy. So there's a little step up and then a big track down for the product. The 1,2 product is faster, right? Because we don't have this whole big thing to go through. We just directly add to the carbonyl carbon. The 1,4 product requires more activation energy, but is slightly more stable. I'll draw it down there. Right. So in the Grignard, with a Grignard or a high energy compound, we already are starting at such a high energy that all we can do is do the fastest reaction, right? Whatever's possible. Okay. As soon as we do that, we drop way down here and we're done, and that's it. If I have a low energy nucleophile, like the Gilman reagent, R2 copper lithium, okay, there's not nearly as much energy difference between the reactant and the products. So that way, if I wanted to do 1,4 addition, which gives us a more stable product because there's no double bond, that's favored thermodynamically. Okay. In other words, 1,2 addition is reversible, okay? Whereas with this high energy Grignard reagent, 1,2 addition is irreversible. So take a look in your workbook for that nice explanation for that. Essentially the real high energy ones. So Grignard and alkyl lithium do direct addition, 1,2. If we want an R group to do conjugate addition, we need a Gilman reagent.